Welcome everyone to PCB Design Basics run by AMB. My name is Christopher Moore and I'll be presenting this topic. So what is a printed circuit board? A PCB. So PCB is a printed circuit board and it's something that you've almost definitely seen before. So there's an example in the top right here. It's these green boards that have a bunch of connections and little markings on them. And printed circuit boards mechanically hold components and electrically connect them together. So they're used in all forms of electronics. So you'll see them in your phone or even in your computer. And they have the advantage of being way smaller in some cases and being more permanent solutions than something like breadboarding. And they also provide better and more controlled electrical characteristics when that actually matters. So ECAD is CAD software that's used specifically for designing printed circuit boards. So ECAD stands for, I think, electronics CAD. And it consists of two major steps. The first step being schematic capture, which is where you place your parts on a schematic and you define how you want different pins of each component to be connected to each other. And then you have the second step, which is board layout, which is where you take physical representations of your components and you connect each of the pins based on how you defined it in the schematic. And in software like Fusion 360, these two steps are linked together so that any changes you make on your schematic will be reflected on your board and it'll tell you exactly how to connect each pin together. So today we're going to be making a board that just combines a microcontroller and this sensor over here. So this sensor is an oximeter and heart rate sensor, and we're going to be using this ESP32 microcontroller to control and get data back from this heart rate oximeter sensor. So to start any design, you'll need a component library. Libraries are things that store parts that can be reused in different designs. Each part has a schematic symbol associated with it, which is associated with the schematic capture step. And each part also has a footprint, which is a physical representation of where it'll be placed on the board. And these libraries allow you to reuse components across completely different designs if you want. So to create a library in Fusion 360, we'll go to this menu up here and just click create a new electronics library. And for each part that we have, we'll need to create a symbol if one's not already made, and also a footprint. And then in this third step, we'll create a new device which combines and associates the symbol and footprint together. So we're going to do that now for this MAX 86916 part, which is the sensor that we're using. So I'm going to switch over to Fusion. You guys can see this, right? Okay. So we're going to go up here and do a new electronics library. And from here, we can create a new symbol. And for the symbol name, I'm just going to use the part number. So I'm just going to copy that and paste it. And just click OK. So now it brings me into this window here, which allows me to actually draw the symbol that I want. So for this symbol, it's just somewhat of a generic integrated circuit. So it doesn't have any special electrical meaning. Like a resistor, you might draw a resistor symbol, or a capacitor, you will draw a capacitor symbol. But for this, it's just kind of a black box. So we're just going to draw a box to represent that. So you can go up to the place menu and click on the line tool. And then this allows you to draw lines on your schematic. So we're going to start this line from the origin here, which is this little cross mark, and the cursor is the slightly darker cross. So we're going to click on the origin and then drag our line to wherever we want to draw our box. And then just left click to place down the line. And when you're done, you can press the escape key to stop whatever you're doing. So if I go back to this presentation, we can see that this part will have 8 pins. And we'll look at the data sheet later to confirm this, but we'll just place down the pins first. So this pin tool, sorry, that's not it. Pin tool over here lets you place down pins. So just click that and you'll get this pin. And you'll see on the pin that there's a little circle, and that's where you'll later connect wires to other components. So you want that to be facing outward from the box that you've created. So you can place that with the line kind of attached to the box that you made, and then just left click to place it. And since we need 8 pins, I'll just do this 8 times. And to place on the other side, to rotate easily, you can just right click and it rotates 90 degrees. And this allows you to place in the other direction. So now these pins are placed. They don't have much meaning. So if you were to look at a schematic and you see $$1, that doesn't have much meaning to you. So now we want to name the pins based on something meaningful. So we know the pin names based on the data sheet. So in order to get those names, we have to search up the data sheet for this part. So we can look up max 86916 on Google and then just type data sheet after to find the data sheet for this part. So we can see I've already looked at this. And the data sheet for a part contains all of the useful information that you'll ever need for a part almost. This one's kind of long, but we just want to go and find the part that shows what are all the pins on this part. There's a bunch of useless information that you probably don't care about, but we can see here that here are a bunch of pins and their descriptions. So we can see we need a VDD pin. So we're going to go back to our schematic. We're going to go to the name tool, which is also in the place section. We're going to click on name, then we're going to click on the pin, and then this brings up this little dialog that allows us to name the pin. So we're going to name this first pin VDD based on the data sheet. And we also have a ground, which is ground, GND. We also have VLED, so we'll name this one VLED. Then there's also another ground, so we'll make another pin for that ground, but we'll probably just connect those together later. And then we have 4 other pins for the control interface. So there's SDA, SCL. There is an INTB, which is an interrupt. And there's finally VREF, which is a reference output voltage, I think. So we have all these pins labeled. So that's a lot of the part already done. So there's still more that we have to do in order to complete this symbol. So if we go down here, so we need to name and add a value to the schematic. So with this part right here, we don't really know what this is. If we were just looking at this on a schematic, it's what could it be? Like, we don't know. So we're going to add a name label to it. So to do that, we have to go up to this top left drop down up here, and this is all the different layers that can be added to the schematic symbol. So what we were using before was the symbols layer, which is where you want to put all these lines and pins. But for text and labels, we should use other layers. So for the name, we're going to use the names layer. And we can label it with the text function. And there's this little pop-up over here. And we're going to add a name label. So this little arrow over here is a special symbol in Fusion or electronics design software. And that specifies that this is a placeholder for a name that can be added later. So we're just going to do this and a name. Oh, I did that wrong. So we're going to do the arrow name, and we can place this on our part. So I think this is a bit too small. I'm going to increase the size there. So we can place this down right over our part. And also we want a value associated with this part as well. So we can do the same thing. We'll go to the values layer, add text, and do the same thing for the placeholder for a value. And we'll place this below the part so that they don't mess with each other. So I think that's everything we need to do for the symbol for this part. So we can just save the library. So I'll just name it library. And we're done with this part. So moving on, we need to make the footprint for this part. So that's information that we can also get from the data sheet. So we're going to go to our library again, and we're going to click on create a new footprint. And we're going to name this footprint something a bit more meaningful. So we have to go to the data sheet and find the package information. And the package is just like the footprint. So we can see at the package information, the package type is 14 OLGA. So the 14 probably corresponds to the number of physical pins. We don't really care. So I'll just copy paste that and click OK. So now we're in a bit different view. So this is the area where you'll actually create what shows up on the final PCB. So we see the package information. We have to find what the actual package looks like though. So I have a screenshot down here. This is directly from the data sheet. It's somewhere in there. I don't really know where it is. I guess I can look for it. Let's see. So there's a lot of useless information. But somewhere in this data sheet, there is a description of what exactly that package looks like. Okay, it's probably near the package information. Okay, actually for this part, I think I'm remembering wrong, but I think we need to actually follow one of these links. So for some reason, they don't provide the layout for this package in the actual data sheet, and we have to follow one of these links. So I think land pattern is what we're looking for. So this is a link, so I'm going to click on this. And here's the information for the recommended land pattern. So we're just going to replicate this in our ECAD software. So to do that, we need to know all these measurements. So we need to know the size of each of these pads. We also need to know the distance between the pads in both the horizontal and vertical direction. So there's a tool to make this a bit easier. Since there is quite a number of pads, there's something called the pattern tool. So first I'm going to switch to the top layer, and we're going to create an SMD pad array. And this brings up this nice little dialog that allows us to place many pads in a certain pattern all at once. So the base name, I'm just going to say P is the base name. And based on this data sheet, it looks like this is a left and right pattern. So I'm going to select left and right sides. The total count of the number of pins, I think, is 14. So if we count, that's 7, 7. So 14 is the total number of pins. And the start index, I'll say, is 1 instead of 0. So for the spacing, so if we look on the right, the spacing that dx and dy represent, so dx is the horizontal space between each row of pins, and dy is the vertical space between each pin. So dx is given by the data sheet as 2.6, and the unit of that is, I believe, millimeters. So we can type 2.6 and change the unit to millimeters, and the dy is 1 millimeter. And conveniently, we can add the name and value in this dialog as well. And also see if generate rectangle does anything. There, so we got our part, and it's all pretty nicely made already. So I don't think there's not much else we have to do for this part. So there's just one last thing we have to do, I think, after my computer loads. But that one last thing is giving a little placement marker to indicate how someone that's assembling this board later on should place this part, because this part looks pretty symmetrical. So how would someone know which way to orient it? Okay, so this is back. So I'm just going to place this down. So we need to tell the person that's making this board which pin is pin 1. So I can see pin 1 is labeled up here. So in order to label that, I'm going to go to the T-place layer. So the T-place layer is something called the silk screen, and that's something that's actually printed on the board when it's manufactured. It's usually in white color on the green background. So we're just going to make a little dot to indicate that this up here is pin 1. So we're going to go to the Draw tab and make a little circle. And just click circle, and then we'll click where we want to add the circle on the screen. So this looks good. Okay, that's not what I wanted. And I'll make the line with 0. I think that makes it a solid circle. There we go. So I'll just click once to determine the center of the location, and then I'll click again to decide the radius. So that looks pretty good. So when someone's looking at this board later, they'll know to orient pin 1 up here with this dot. So I think that's everything for our footprint for this part. So I'll just save that. Go back to the presentation. Actually, there's one more thing. So we need to make a keep out. A keep out is a layer that prevents parts from colliding with each other when you place them on the board. So when the software sees keep out areas that are overlapping with each other, it'll go crazy and warn you to stop you from buying a board that has overlapping components. But we have to define how big the keep out area is on this part. So we'll just kind of make it the same size as this bounding box that's already made for us. So we have to draw a rectangle on the keep out layer, which is layer 39. So I'm not going to be really precise with this. I'm just kind of click over here and draw a rectangle around everything. And there we go. We have a keep out layer. So if another part is nearby and the keep out layers intersect, the software will go crazy and warn you. So I think that's actually everything that we need to do for this part. So the last thing is to make the device from the footprint and the symbols that we've already made. So we're going to do the same thing up here and click create new device. So I'm going to use the same part name up here, which is Max 86916. And from here, we need to add our footprint and our symbol. So to add our symbol, we'll go up to this add part button, click add part, and our only symbol so far is this. So we'll click this and click OK, and we'll place this near the origin. So we placed one part, and we can click escape to stop placing more. And now we want to add the footprint that we made. So we'll go down to new over on the right side, add local package, and we'll click on the only package that we currently have. So now we have our symbol and we have our footprint. So the last thing to do, or one of the last things to do, is to connect the pins that we define on our symbol to the physical pins on our board layout. So to do that, we have to go to the connect button, and it shows all the pins that we defined on our symbol and all of the pins that we defined on our footprint. So to connect these, we need to use the data sheet. So we'll go back to the data sheet, and I remember there was a nice section that showed each of the pin numbers and their corresponding name. So we can just use this table to determine which pins to connect over here. So I'll just go through this. So pin 1 is no connection, which is NC. 2 is VLED. So I'll click pin 2, click VLED, and then to connect. And now that connection is made over here. And pin 3 is P ground. So I'll click pin 3 and P ground and connect. Now pin 4 is VLED again. So to attach another pad to the same pin via VLED, we just click on the pad, click on the connection over here, and then click append. So now we see that VLED is connected to both pads 2 and 4. And now pin 5 is normal ground. So just connect. 6 is VDD. So 6 and VDD, connect. 7 is no connection, so we can ignore that. 8 is VREF. So connect. 9 is SCL, 10 is SDA, and 11 is INTB. So that's it. We don't need to worry about all these pins. These are just connections, so we can just leave them for now. And we just click OK. So now, if we really wanted to, we could use this part in our design. There's still one more thing that we want to do, I think, and that's to add a prefix. So in the name, Fusion will automatically name your parts with a prefix and a number that is a unique identifier for the part. So prefix, you'll see on boards for like resistor parts, you'll see R as the prefix. For capacitors, you'll see C. For something generic like this, we can just use U, which is kind of a general integrated circuit. And we'll just click OK. So that's everything I think we need to do for this part. So now we can actually start to make our electronics design. So we can go back to Fusion and click New Electronics Design from the same tab that we made our library before. And from here, you can see that there's options to make a schematic and a PCB, which is the layout. So first we have to make our schematic. So click New Schematic. I'll just close out all these side windows. And this is kind of similar to what we saw when we were making our footprint. It's the same white background, and you'll see also that there's some similar common layers. So we want to add our sensor part to the design now. So we can go up to the place section and click Add Part. And we'll see a bunch of libraries that are already made and that are kind of included with Fusion, but we want to go down to the library that we made. So mine was called Library. So this is the part that we made. So I'll just click that and I'll click OK. Now we can see that our part is hovering here. So we'll just place this near to the origin. Click Escape to stop placing more of the parts. And you can see the part here. Okay, so sorry, Nate, I stole your mouse, but we can go back to the schematic and we can navigate around our schematic. So to like drag, you use the middle click, which is just pressing down your scroll wheel, and that lets you drag around stuff, and you can zoom with by scrolling up and scrolling down. So now we've added that to our schematic. We should probably add some other parts. So I already prepared the library with the microcontroller that's already made, since it's kind of tedious to make. So if you go to this link or scan this QR code, you can find that library. So I'll post it in the Zoom chat for those that are watching on Zoom Live. And you can go to that link, and I think it's a Google Doc. And if we go to the pre-made library, you can download the library that I made already that has the microcontroller schematic, symbol, and footprint already. And we can try importing that into our Fusion design. Okay, I guess you have to enter your email. Yeah, PCB Workshop resources, you'll find that link. And you should be able to download that, and we can try importing it. Okay, so I downloaded the library. So we can go to Fusion. And we can import the part that we want. So to add this library that we just downloaded, you can go to the Manage tab, open Library Manager, browse for the library file. So mine is just right here. It's called library. And should be able to use that library now. So we can import the component by just clicking on one of these and clicking import, and scroll down to find the library that we just imported. So there's a bunch of extra components here you don't need to worry about. But the component that we're looking for is this ESP32-C3, which is the microcontroller that we're going to put on this board. So we'll just select that. Sorry, I was in the wrong library. So we're going to import ESP32-C3, and you'll see that we have this symbol, and also there's the footprint here, and it's already connected for us. So we can go to the schematic that we were using before, which got deleted for some reason. So I'll have to remake the schematic because Fusion crashed for me. Okay, so we're going to add the parts that we made. So we have one of these libraries, is it? So we have the sensor that we made before. It's already placed up here for some reason. And we also want to add the microcontroller part that we have. Just place over there. And now we can start connecting some stuff up. So I'm going to move this over to the right. We can start connecting some of these pins. So to connect pins, we want to use the net tool, which is kind of just a wire. So we can connect this SDA, which is a data line, to some IO pins. So this microcontroller is a bit special, and you can basically use almost any pin that you want to do IO like this. So we can just click on the pin, drag the line where you want it to go, and then click on the destination. So we've connected these three lines together. So these are just our data lines, but we also need power for this device. Luckily, there's a 5-volt output over here and a 3.3 volt output over here. I think the datasheet says that VDD needs to be 3 volts or your logic level. So we're going to connect this 3 volts over here to this VDD, but we're going to do it a bit differently for power related stuff. So for power, there's something called supply pins. So we're going to search for plus 3V3. Okay, let's try ground. So ground, we can see power symbol. We can just click that to get our ground symbol, and we can place that. So ground usually has the pin facing up and the arrow kind of pointing down. So you can place that next to your grounds, but kind of below it. And we'll use net to connect ground to our ground symbol. And we also want our 5 volts, plus 5 volts. So you guys should have access to this power symbols library, which is kind of included already. So we're going to use plus 5 over here. We might not actually use the 5 volts for anything. And now we have to get our 3 volts somehow. So this power symbols library has plus 3.3 volts. I'm going to use that symbol for the 3v3. I'll kind of place that out here so that the wires don't overlap. And VDD will also get 3 volts. So we'll just connect those together. And now we need to do something about this VLED. So I'm not sure what voltage we need exactly, but if we go to the data sheet, we can find out. So VLED is over here. Just go up to kind of the electrical characteristics section, and we can figure out what voltages VLED supports. So these are the absolute maximum ratings. We probably want something more like the recommended. So power supply for VDD actually is, so I got that wrong. So VDD is supposed to be 1.8 volts with the range from 1.7 to 2. And the LED is supposed to be from 3.5 to 5.5. So we actually don't need the 3 volts. So this is wrong. So I'm going to delete this. We actually need the 5 volts attached to VLED. So we're just going to use those power symbols again to connect VLED to plus 5 volts. But we don't have a plus 1.8 volt supply anywhere. So that's something we're going to have to solve right now. We're going to look for a power supply. So when I search for components, I generally go to places where I can actually buy them from, since components aren't that useful if you can't actually buy them. So my preferred supplier is called DigiKey, and they have a ton of different products that you can buy, and they also provide data sheets like right next to the product, so they're very easy to evaluate if the component's good for you. So we need to look for power management kind of stuff. So I know that it's under this integrated circuit section, and if we scroll down to PMIC, which stands for Power Management Integrated Circuits, and we want a voltage regulator to power our chip. And we're looking for a voltage regulator in a linear kind is what we want for this case. So when we go to DigiKey, we can see there's a bunch of filters up here, and this will allow us to find parts that are actually useful to us. So you can see that there's tons of parts. So there's 691 pages with 100 results per page. That's way too many to look for. So we're going to look for something that we want. So voltage output, we want 1.8. So we're going to scroll down and just choose 1.8. And voltage input max. So we have both 5 volts and 3 volts available to us. So we're going to go with the higher one, which is 5 volts. And we can choose multiple by doing shift click. And that selects a bunch of ranges of parts. So we can use any regulator that has a max voltage of 5 volts or higher. So we're going to filter that. And we can see that there are a bunch of parts here that we can use. So this first one has a 1.8 volt output, and it can do max input voltage of 5.5 volts, which is okay for us since we have a 5 volt supply and that is below 5.5. And this can output 150 milliamps of current, which is almost definitely fine for this sensor that we're using, but you can check in the data sheet if you want. So we're going to use this part. And if you look on that workshop references sheet, so I have a very similar thing already chosen, so either one will work. And you'll see on this site that all these statistics, how you can buy it. And if we scroll down to documents and media, you'll see the data sheet and also something down here, the EDA/CAD models. And with that, we can, if we click on that, we can download the pre-made library already for us. So we don't have to make all that stuff that we did before and go through that pain. So we can click download and scroll down to Fusion, and that will allow us to download it. So I think you have to make an account to do that. So I've included it in the library that you already imported before. So we can just add that power supply from the library that you can find in that reference sheet. And that part is called MIC, and then it has some numbers. So then just add it just as we did before. Just click OK, and we can place it down kind of anywhere we want, but you want to group components that are related to each other together. So this VIN pin, we want to connect to the 5 volts over here. So we're going to do the same thing, add our supply with the power symbols, plus 5 volts. And we need to connect ground and our V out. So our V out is 1.8 volts. So we can add a 1.8 volt symbol. And we're going to need it down here as well. And we need ground again. So I'm just going to copy it from somewhere else. Now we just need to connect this all up with nets. So V out goes to 1.8, ground goes to ground, V in is 5 volts. This enable pin can be left unconnected and it'll still work all fine. So we don't need to worry about that. Connect 1.8 volts over to VDD, and that's nearly everything. So nearly everything is already connected, but there are some specific details that we need to worry about for this chip over here. So if we go back to the data sheet for that chip, if we scroll down a lot, I think there is a application example somewhere. A typical application circuit. So not all data sheets will have something like this, but this is something nice to kind of reference if you're missing anything or you're doing something wrong. And you'll see here that we're supposed to have capacitors on the inputs for the power, for both power, VDD and VLED. And we're also supposed to have these pull-up resistors on the SCL, SDA, and INTB lines. And that's supposed to be connected to the same voltage as, or the voltage for the IO pins that we're going to be using. So we need to get a resistor symbol in our schematic. Resistors are really common, so you'll find that symbol is already somewhere in the pre-included libraries. So if you just find the resistor library, and you can find a bunch of parts already made for you. So all these different chips, so R_chip, and then you'll see these 4-digit codes. These 4-digit codes just correspond to the size of the part. And these parts like 0402 are super, super tiny. So we're not going to use those. We're going to stick to something like 1206, which is something that you might actually be able to assemble by hand. So we're just going to click on that, and you'll see that there's a resistor symbol, and we can just rotate that and kind of put them where we want. So we need to connect resistors from SDA to high voltage and do the same for SDL and INTB. So we're just going to place 3 resistors, but we need to assign them a value now. So somewhere around here, there's a value command. So over in modify, I think, yep, there's value, also as a shortcut of V, and we need to add a resistor value to indicate what size of resistor we're going to use on these pads. So just click on the part and we can add a value. So I think 4.7K would be a good value. You can check that using other typical application circuits. We're just going to use the same value for each of these. And we're going to connect one side of these resistors to plus 3.3 volts. So we're going to do plus 3.3. And connect all these nets up to the 3.3 volt supply. And now each of these resistors will go to SDA, SEL, and INTB. So this first one we'll say goes to SDA. The second one we can bring down to SCL. So this looks kind of weird with the lines overlapping, so I'm going to avoid that and go to the side. And then this third one we can bring down to INTB. So that's all done. So we don't need to worry about these resistors on the left anymore. We just need to worry about these capacitors now. So capacitors are also really common. So we're going to find a capacitor library that's also pre-included. and we're going to use the same 1206 package. And we just need to place this down. So I believe one resistor goes on the output of VREF, and then there are two capacitors for each of the power inputs. So I'm going to kind of shove these in somewhere. So put those there. I'll move them a bit more later. Put those two there. We can use the move command to kind of space things out a bit more to make it easier to work with. So now we need to connect these capacitors in parallel between VDD and ground, and also VLED and P ground. So we're going to just connect these up. And if you want to merge, just asking if you want to merge this net that you created into the supply, which we do. So now these capacitors are connected in parallel between VDD and ground. Now we need to do the same for VLED. So we just move this ground down a bit more. And connect these in parallel in the same way. Now there's this one last one, VREF. So let me check the application circuit, and it says to connect a capacitor between our VREF and ground. So I'm going to take this, just connect that over and connect it to ground. Or I could alternatively just make another supply symbol, bring it over here, but I'll just do it like that for now. But we also need to add capacitor values for each of these capacitors. So we'll use the same value command. Just click on it. So I think this is 1 microfarad. So 1 UF, and then these two 0.1 microfarad, 4.7 for VDD. And for VLED, it will be 0.1 microfarad and 10 microfarad. So I think that's everything that we need to do for the schematic. So now we can move on to layout of our board. So we can go up to the top left and just click switch to PCB document. And we'll see a sample outline of our PCB, and we'll also see these parts down here. So each of these parts corresponds to something that we already added on our schematic. So you can see this is the microcontroller, here's the sensor, and here's a bunch of resistors, capacitors, stuff that we can organize now. So we're going to organize this, placing components that have connections close together. So you can use the move command and move them onto this black area, which is the board. So I'll just place that there. This has a lot of connections, so I'll just place that there for now. This power supply, throw that there. And these resistors will go for each of the data lines. Okay, so these white lines here are called air wires, and those are just the same nets that we connected in the schematic. Each of those air wires corresponds to a connection that we need to make. Okay, so we want to reduce the crossings of these air wires so that it makes it a bit easier for us to add traces between each of these pins. So we're going to just move this around, and if you can see different orientations that have more advantageous configurations, just move it there. so that we can connect them more easily later. So that looks okay. This probably wants to be over here. And it's not super vital, especially for a component like this, where you place stuff or how close you place stuff. But you do want to keep it not too cluttered, so that's kind of easier for you to assemble later on. Okay, so that's good enough for now, I guess. So let me move this around some more. So it's kind of messy, but let's try and route it with the connections that we have. So to route, we're going to use this route manual tool, and it'll make this pop up, and we can choose a bunch of different properties. So the trace width is how wide you'll see it come out. So like if it's 6 right now, I'll just double that to 12, and you'll see that it actually doubles in thickness. And then there's also a bunch of other properties like the trace bend. So right now, if I try and go up, it'll do a 45-degree angle, or I could do squares like this, or I could do a straight line, or even curves, a bunch of different curves. So I prefer this kind of angled thing because it looks kind of nice and it's pretty clean. So we're just going to follow these air wires and connect everything together that has an air wire. So I see this 3-volt pin, and there's an air wire going up to each of these things. So I'll just place down a route to connect each of these. Now the air wires have disappeared, and we don't need to worry about them anymore. And each of these, so this needs to go all the way down to this pin. So we can just do that for now. We might need to move that later. And then this one needs to go over here. So to prevent these from crossing, I'm going to swap the positions of these two components. Okay, there's something preventing me. So there's this route already made. It's kind of hard to move components that are already routed. So we can use the rip up command to rip up these traces that we've already placed. So I'm just going to swap these positions, and that might make it a bit easier for us to route now. So just click on one and then click on the pad where it's trying to go, and Fusion will do some of the slight bends that you might have to do to make it around stuff. So right now I'm kind of having trouble getting through all these pins here. So as a solution, I can just go to the other side of the board. So this will make a hole through the board and make a connection from the top layer, which we're currently editing, to the bottom. So red corresponds to the top layer, and now we're on the bottom layer, which is blue. So now we don't have to worry about hitting any of these pins when we make a route. So we'll just route it over here, and we can middle click again to make another via that will go to back to the top layer, and we can complete that net. So we just have to keep doing this over and over again. It gets kind of repetitive. We can just connect all these. So there's some really common connections like ground. And you can actually do big pours of copper instead so that you don't have to manually connect them, but it's a good idea to do it like this. So I'm having trouble getting through again, so I'm going to do that trick with the vias again. Just middle click to make the via to go onto the other side, and then you can come back with another via. So I might normally spend more time trying to organize these components a bit better instead of just using vias all over the place. Because when you manufacture this, some manufacturers don't like if you use too many, but in this case, it doesn't really matter. So for some reason, I can't get there. So let's try smaller trace. Okay, that's interesting. Well, skip that for now. I'll just do these 5-volt connections down here. So I'm trying to get from this hole over here. So you might think you could just use a via, but it'd be even easier. We can just start on the bottom layer instead. So we don't have to worry about any of this. Since it's already a hole, using a via is kind of redundant in this case. And we can see that this highlighted slightly brighter area is the same net. So we can just directly connect that like that. And then this is another thing that we need to kind of go really far. So we'll try using a via again. So it seems like we'll have to actually go around to get where we're trying to go. And you'll see that Fusion actually does some rerouting for you, so you don't have to worry about the specifics too much. So yeah, this is pretty repetitive, and I see we're running out of time a little bit. So if you just finish that layout stuff just by connecting all those wires, it's a bit of a puzzle. It can be fun sometimes, but reorganizing these components will help a lot more so you don't have a complete mess like this. But the last thing, after you completely finished all of your routing and connecting all the air wires, you won't see any more of these little white lines, and that's how you know you'll be done with the layout. You can actually see your final product by going to the manufacturing tab. And the manufacturing tab lets you generate the files that you need in order to actually send it off to a manufacturer and get this board produced. And we can see that this little preview up here, and we can see the board that we kind of made over here. So we can see all the connections, and we can see all the different holes and all the different pads where you would actually connect different components. So this is just the top side. And I think we have some traces in the bottom. And you can see all the different connections you made. And you also see these white lines, which are called the silk screen. So we can see that dot that we placed before in order to indicate that this is pin 1. So if you were looking at this board that's already been manufactured, you can't actually tell that that's pin 1 without that dot. So someone that's assembling it might actually place it the other direction. So with this dot that's showing up on the white, which is called a silk screen, whoever's assembling it can put it in the right way. Yeah, so I think that's really everything for the design of a printed circuit board. If you wanted to actually finish this, it would take a bit more work, and usually designs will be a lot more complex, and there's even a lot more layers involved sometimes. So this is just a 2-layer board since we're using a top and bottom side, but even there might be something where you have 4 or 8 or even 12, which get super complex, though it probably won't run into anything like that. So yeah, that's everything.